Okay, good morning, everybody. Today, we are going to start the next concept, classification of magnetic materials. Generally, the magnetic materials which are having permanent dipoles and which are not having permanent dipoles. Generally, we know that. So, in the magnetic materials, the magnetic dipoles are existing. That is because of here the orbital motion of the electron and the spin motion of the electron, which is responsible for the magnetic property of the given material. So within the magnetic material, so permanent magnetic dipoles are existing, and in some magnetic materials, permanent dipoles, magnetic dipoles are not existing. So based upon the existence of permanent magnetic dipoles, so they're classified into broadly two categories. So those materials which are not having permanent dipoles, which are known as diamagnetic materials, and those materials which are having permanent magnetic dipoles are classified into para, ferro, antiferro, and ferrimagnetic materials. So in diamagnetic materials, they're not having any permanent magnetic dipoles. So coming to see here, this picture here, so this is a diamagnetic material. Whenever H is equal to 0, there is no existence of permanent dipole. But under the application of an external electromagnetic field, then the dipoles are oriented in a direction opposite to the direction of the direction of the upward magnetic field. Okay, next, but coming to para, ferro, antiferro, and ferrimagnetic materials, say in these materials they're having permanent magnetic dipoles, but their alignment of dipoles, the direction of dipoles, and magnitude of dipoles, okay, based upon all these, they're again classified into para, ferro, antiferro, and ferri. Now here, if the alignment of these dipoles which are in random direction, they are known as the para. So coming to this one, these are paramagnetic materials. Say in the paramagnetic materials, and in the absence of external magnetic field, all the permanent dipoles which are oriented in random direction. So if these permanent dipoles which are aligned in random direction, so that material is known as paramagnetic material. Otherwise, if these permanent dipoles which are aligned, okay, in the uniform direction, so that means they are known as ferro, antiferro, and ferri. That means coming to here, ferromagnetic, ferrimagnetic, and antiferromagnetic, consider any domain within the material. So even H is equal to 0, consider any domain in the any domain region, all the dipoles are aligned in a uniform direction. So that is all the dipoles which are aligned in a uniform direction. That means the direction of the domain is changed from one domain to another domain, but within the domain, all the dipoles which are uniformly aligned. So alignment of dipoles is uniform. So coming to here, ferromagnetic, so within this domain, all the dipoles are in uniform direction. Coming to antiferro, so consider this domain region. In this domain region, these dipoles are okay in uniform direction. Actually, uniform ga unnai anni kuda. So of course, opposite direction unnai, but ikkadaithe within this domain, so the dipoles are in opposite direction, but which are having different magnitudes. So magnitude of dipoles, so which are having same magnitude, that will be observed in antiferromagnetic materials. Say in the antiferromagnetic materials, within each domain, the dipoles are aligned, okay, and the magnitude of the dipoles which are having equal magnitude, but which are aligned in opposite direction. Okay, whereas in ferrimagnetic materials, within each domain, the dipoles are of different magnitudes, which are aligned in opposite direction. Yeah, coming to each one. First one, diamantic materials. So basically, materials which one placed in a magnetic field can acquire feeble magnetism in a direction opposite to that of the applied magnetic field. Such materials are known as diamantic materials. So generally, in the diamantic materials here, the property of the diamantism was discovered, okay, when actually Anton Bregmans observed in 1778, okay, that is in bismuth material. So because bismuth is the best example of the diamantic material. So here diamagnetic materials are repelled by magnetic field because an applied magnetic field creates an induced magnetic field in them in the which is in opposite direction, causing a repulsive force. Yeah, coming to this here. So all the dipoles which are oriented in the opposite direction of the direction of the applied magnetic field. It is a very weak form of magnetism. The property of the diamagnetism, it is a very weak form of the magnetism that is induced by a change in orbital motion of the electrons. That అంటే change in orbital motion of the electrons due to an applied magnetic field. The magnitude of this induced magnetic moment is very small, and its direction is opposite to that of the applied magnetic field. That means under the application of an external magnetic field, the dipoles are oriented in an opposite direction, okay, within that material. So what are the properties generally? See, these diamagnetic materials, which are, okay, having susceptibility and relative permeability values. The magnetic susceptibility is negative and small. Psi is equal to negative and which is small. Temperature has no effect on the susceptibility of these diamagnetic materials. Say the relative permeability is less than 1 but positive. So this means lines of magnetic field become less dense in the material than in the air. Actually coming to this one here. So whenever the diamagnetic material is placed between the poles of the magnet, that means within which is placed in the magnetic field, the magnetic field lines are not passing through this diamagnetic material. So which are expelled by these magnetic lines of force, magnetic field lines, which are not passing through this diamagnetic material. Because this diamagnetic material which opposes the magnetic field lines. That means the magnetic field lines are repelled by that means expelled by this diamagnetic material. So here, coming to the next one, in general, the substances whose atoms possesses paired electrons exhibit to diamagnetism. Which type of substances, which type of atoms which are exhibiting this property diamagnetism? There are some exemptions like copper to this behavior, of course. Yeah, bismuth. What are the examples of diamagnetic materials? Bismuth, zinc, copper, silver, gold, diamond, sodium chloride, water, nitrogen, and hydrogen. So because here bismuth is and mercury also. Mercury is a very best example. Bismuth and mercury, which are best examples of the diamagnetic materials. Because in the mercury, okay, we have to observe the property of this diamagnetism, and also it is a superconducting material. The property of this superconductivity was also observed in this diamagnetic material, that is mercury, whenever it is cooled down to very low temperatures. So that is the phenomenon of superconductivity. Yeah, coming to here, second one, paramagnetic materials. So what are paramagnetic materials? When the material is subjected to the applied magnetic field, the magnetic dipoles tend to align in the direction of the field, and the material becomes feebly magnetized. So that means here, yeah, coming to this one, and in the absence of the magnetic field, all the permanent magnetic dipoles which are aligned in a random direction. But in the presence of the external magnetic field, all these permanent magnetic dipoles, which are aligned in the direction of the applied magnetic field. So that too, if the material, okay, just like what are the examples of paramagnetic substances? Aluminum, magnesium, tungsten, platinum, oxides of copper, cobalt oxide, iron oxide. So these are examples of a paramagnetic material. Suppose a paramagnetic substance material is placed in the external magnetic field. That means by using the here, this is the paramagnetic material which is placed between the two poles of the magnet. That means which is placed in the presence of an external magnetic field. The magnetic field lines are all to passing through the material. That means this paramagnetic material which allows these magnetic field lines through it. That means here paramagnetic materials have some unpaired electrons. Due to these unpaired electrons, the net magnetic moment of all electrons in an atom is not equal to 0. Hence, atomic dipole exists in this case. So because in these paramagnetic materials, they're having single electrons, unpaired electrons. So these unpaired electrons which are having magnetic moment, because we have to calculate the magnetic moment of the electrons due to orbital motion and due to spin motion. So if it has two electrons, paired electrons, then the magnetic moment of the two electrons cancelled because which are in opposite directions. That is possible in case of diamagnetism. Okay, so these diamagnetic materials which are having possesses paired electrons. In case of paired electrons, these two electrons which are moving in okay, opposite directions. So one electron is moving in clockwise direction and second electron is moving in anti-clockwise direction, so that the magnetic moments because of the clockwise electron and anti-clockwise electron both are cancelled because both are in opposite direction. Whereas in case of the material which it has only single electron or unpaired electrons, it has the net magnetic moment. So, and all electrons in an atom is not equal to 0. That means the net magnetic moment of all these electrons is not equal to 0. Okay. That too, on applying external magnetic field, the atomic dipole aligns in the direction of the applied external magnetic field. In this way, paramagnetic materials are feebly magnetized in the direction of the magnetic field. That means these materials, paramagnetic materials, which are magnetized in the direction of the applied magnetic field. Coming to properties, the susceptibility, magnetic susceptibility is small and positive, and the relative permeability is greater than 1 but small. So these substances have unpaired electrons in their valence orbit and temperature dependence. So actually, this magnetic susceptibility decreases with the magnetization. So here, actually, this is a Curie's law. Actually, it allows Curie's law. The magnetic susceptibility is inversely proportional to absolute temperature. So psi versus temperature and one by psi versus temperature. Okay, so these are two curves actually. So this law is called Curie's law, and C is called Curie's constant. Okay, coming to here, sector next one, ferromagnetic materials, because these are very important. So materials which one placed in an external magnetic field can acquire a feeble magnetism in the direction parallel to the direction of the applied magnetic field. So they are strongly magnetized by the applied field. Such materials are known as ferromagnetic materials. Say here. So in the absence of external field, the dipoles, which are magnetic dipoles, which are okay, which are somewhat they are magnetized even in H is equal to 0. Suppose the H is applied, the external magnetic field is applied, so all the dipoles are aligned in the direction of the applied magnetic field. Okay, even if the applied magnetic field is removed after a magnet is removed, that means if the applied magnetic field is removed, but here the magnetization not becomes 0. Here that means the dipoles which are aligned in the direction of the field, applied magnetic field. That to here, whenever the given ferromagnetic material is placed in the magnetic field, that means which is placed between the poles of the magnet, that is placed in the external magnetic field, all these field lines are passing through this material easily. So that's why here a ferromagnetic material contains permanent atomic magnetic dipoles that are spontaneously oriented parallel to one another, even in the absence of an external field. సో హెచ్ అప్లై చేసి మనం రిమూవ్ చేసినా సరే హెచ్ అప్లై చేసినప్పుడు సో ఆల్ ది డైపోల్స్ దట్ మీన్స్ ఇఫ్ ద మ్యాగ్నెటిక్ ఫీల్డ్ is applied, all the dipoles are strongly oriented in the direction of the applied field. Once all these dipoles within the material, they are strongly magnetized, even though if the applied field is zero is removed, but their orientation is not removed. Okay, that means here a ferromagnetic material contains permanent atomic magnetic dipoles that are spontaneously oriented parallel to one another even in the absence of an external field. These materials will retain their magnetization for some time even after the external magnetizing field is removed. If the external magnetic field is removed, but it retains their magnetization for some time. A magnetization కొంత టైం అది దాంట్లో ఎగ్జిస్ట్ అవుతుంది. So what are the examples? Iron, cobalt, nickel, gadolinium. So these are best examples of the ferromagnetic materials. Coming to the properties of the ferromagnetic materials, their susceptibility is very high. Magnetic susceptibility is very high, and which is positive. The relative permeability is also very high. So lines of force are very dense in ferromagnetic substance. Yeah, here the lines of force, the magnetic field lines are easily passing through this ferromagnetic material, because here these ferromagnetic materials which are having magnetic domains. So that is domain theory. By using this domain theory, just you have to explain the ferromagnetic property of the given material here. Next, ferromagnetic substances exhibit hysteresis. It is very important concept. Okay, hysteresis, which are temperature dependence. Their susceptibility is very high and constant up to a certain temperature according to equation psi is equal to c by t minus tc. Yeah, here their susceptibility is increased. Yes, their susceptibility versus temperature. So it follows Curie's law here. Psi is equal to c by t minus t theta or t minus tc here. So here the susceptibility is increased. Okay, up to a particular temperature, that is Curie's temperature. Above the Curie temperature, the susceptibility is gradually decreases. So it follows okay, Curie's law actually. Psi is equal to c by t minus theta, or psi is equal to c by t minus tc. When the temperature of the ferromagnetic substance is increased above the temperature called Curie temperature, thermal agitations dominate the existing interaction between the electron spins, leading to randomization of the dipoles. That means here, thus the spontaneous magnetization is lost above Tc. If the temperature is above this Curie temperature, so it loses the property of the ferromagnetism, but it turns into paramagnetic material. Okay, so that is very important, because the two, these ferromagnetic materials which are exhibiting the property of the property of spontaneous magnetization and hysteresis behavior. So what is hysteresis behavior? So which is okay, we will see that this concept okay in our next class here. So coming to antiferromagnetic materials. Next one, antiferromagnetic materials. So in the antiferromagnetic materials, these are here all the dipoles, neighboring atomic magnetic dipoles, which are having equal magnitudes, but which are oriented in opposite direction. Yeah, coming to this picture here, so these are these blue color okay, blue color dots which indicates here this is O2, okay, and Mn2 plus here. This is for antiferromagnetic materials. What are the examples? FeO, MnO, and Cr2O3. So these are examples of antiferromagnetic materials. Because what are antiferromagnetic materials? Materials in which the neighboring dipoles, which are having equal magnitudes, but which are oriented in opposite direction. Okay, such material is known as antiferromagnetic material. So in this one here, it is Mn2 plus and O minus here, Mn2 plus and O minus. So these are these atomic dipoles which are oriented in opposite direction. Yeah, these are oriented in opposite direction actually. So and net magnetic moment is 0. The spin alignment is in anti-parallel manner. Okay, opposite direction. Susceptibility depends on temperature. So the susceptibility goes to maximum value. at a particular temperature, that is Niels temperature. Okay, if xi is equal here, it follows the xi is equal to c by t plus theta. The susceptibility of this antiferromagnetic material goes to maximum at Niels temperature, a particular temperature called Niels temperature. If the temperature is above the Niels temperature, the susceptibility goes to decreases. Okay, and initially susceptibility increases with increase in temperature, and beyond the Niels temperature, the susceptibility decreases with the temperature actually. Okay, next at Niels temperature, susceptibility is maximum. So these are the alignment of the dipoles. So that means if all the neighboring dipoles which are having equal magnitudes but are oriented in opposite direction, okay, that is observed in antiferromagnetic materials. But coming to next one, classification of ferrimagnetic materials. In the ferrimagnetic materials here, already we know that here, yeah, coming to this one, if all the neighboring magnetic dipoles which are having different magnitudes but which are oriented in opposite direction. So if all the neighboring magnetic dipoles, okay, which are oriented in opposite direction with the different magnitudes, okay, with the different magnitudes, that picture we will observe in this here in this one. So all Fe2 plus have spin magnetic moment. So half of Fe3 plus have spin magnetic moment in one direction, and the remaining of which, okay, in other direction actually. So these ferrimagnetic materials are again classified into, of course, these are also called ferrites. These are classified into cubic ferrites, hexagonal ferrites, garnets. Okay, so these ferrites are classified into these three actually: cubic ferrites Me Fe2O4, hexagonal ferrites AB12O19, garnets M3Fe5O12. Okay, so special type of ferro and antiferromagnetic material. So generally oxides in nature, ionic in nature actually. So because these are three actually, we have cubic ferrites, hexagonal ferrites, and garnets. So we have generalized the properties of these three here, generalized here. So ceramic in nature, so high resistivity, that means they act as insulators. These ferrites are act as insulators, and the spin alignment is antiparallel but a different magnitude here. That point is observed in this picture also. So which are having different magnitudes. Okay, and but which are in opposite direction. So they possesses net magnetic moment, also called ferrites. General formula Me2O4. Here Me2O4, only one is given, the remaining also there. Susceptibility is large and positive. So ferrous ferrite to nickel ferrites are examples of the ferrite materials. Yeah. Now coming to, so these are about here types of magnetic materials. So finally, we have to conclude that the magnetic materials are classified into two types, depending upon the existence of the permanent magnetic dipoles. If the those materials which are having permanent magnetic dipoles, they are known as para, ferro, antiferro, and ferrimagnetic materials. So those materials which are not having permanent magnetic dipoles, which are known as diamagnetic materials. So mainly they are classified into two categories: diamagnetic materials which are not having permanent dipoles, and para, ferro, antiferro, and ferrimagnetic materials which are having permanent dipoles. But in these para, ferro, antiferro, and ferri, finally their okay, the alignment of the permanent dipoles and the direction of the dipoles and the magnitude of dipoles are different in each okay category, that is para, ferro, antiferro, and ferrimagnetic materials. So in the paramagnetic material, all the dipoles which are oriented in random directions in the absence of the field. In the presence of the field, they are oriented in the direction of the field. Whereas in case of ferromagnetic materials, all the dipoles okay which are oriented in the same direction, okay, which is in the direction of the applied magnetic field. Whereas in case of antiferro and ferri, in case of antiferromagnetic materials, all the dipoles which are having same magnitude, which are oriented in opposite direction. Whereas in ferrimagnetic materials, all the neighboring dipoles which are having different magnitudes, but which are oriented in opposite direction. So that is about here this classification of these magnetic materials. Coming to here, the ferromagnetic materials which are having the property of hysteresis behavior and spontaneous magnetization. So a scientist Weiss, he proposed a theory in 1907. So this theory was proposed by Weiss in 1907. That theory is here called domain theory to explain about hysteresis properties, hysteresis and the properties of ferromagnetic material. A scientist Weiss in 1907 he proposed or introduced a theory that is called domain theory. That means what is this domain theory here? So any consider a ferromagnetic material. So you will take any ferromagnetic material. Definitely, it is consisting of magnetic domains. What is a magnetic domain? A ferromagnetic material is divided into a large number of small regions. Is called domains. Yeah, this is the ferromagnetic material. Just consider iron or cobalt or nickel, whatever it may be. So consider any one of the ferromagnetic material which is mainly consisting of a small regions. Each region is definitely consisting of atomic dipoles, atomic magnetic dipoles. Consider this is one region. In this region, the atomic dipoles are oriented in upward direction. Say in this region, it is also, this region is called magnetic domain. So consider to the neighboring region, it is also a region, it is also domain. But in this domain, the magnetic dipoles are oriented in downward direction. Okay, so that means domain is nothing but it is a region, a large number of small regions. Domains are nothing but large number of small regions. Okay, so which contains the magnetic dipoles, atomic magnetic dipoles. Each domain is spontaneously magnetized. Okay, the direction of magnetization varies from domain to domain. So this is domain, this is one domain, this is another domain. So within this ferromagnetic material, the direction of the each domain is different. Okay, and the net magnetization is 0 because domain direction. Okay, next domain direction rendu వేరుగా ఉన్నప్పటికీ కూడా ఆ మెటీరియల్ లో నెట్ మ్యాగ్నటైజేషన్ net magnetization 0 అయిపోతుంది actually. In the absence of an external magnetic field, that is possible. In the absence of an external magnetic field, the net magnetic moment or net magnetization of all these domains is 0. But when two domain separates by a domain wall or black wall, these are domains. Each domain is definitely separated by a domain wall or black wall. So when the magnetic field is applied to ferromagnetic material, the magnetization, the magnetization is produced by two ways. So suppose you have to apply the external magnetic field to this ferromagnetic material, which is consisting of magnetic domains. So which is magnetized. Okay, that means the magnetization is produced in this ferromagnetic material by using two ways: by the motion of the domain walls and by the rotation of the domains. So by the motion of the domain walls here, that means here domain actually motion of the domain walls, the motion of the domain walls and the rotation of the domain walls. The weak magnetic field is applied. The domains having dipoles parallel to the applied magnetic field increases in area by the motion of the domain walls. Here, whenever field is here, V is equal to 0, there is no field, there is an external magnetic field. So all these indicates the the domains which are existing in the ferromagnetic material. Suppose if we have to apply weak magnetic field, then so consider here. So if you have a weak magnetic field, that too the direction of the magnetic field which is parallel to the direction of the which domain. So that domain increases its size. So that means those domains which are having the direction parallel to the direction of the applied magnetic field, those domains are having tendency to increase their areas. The size of the domain is increased. That picture is also observed, this one here and this one. So each domain is magnetized in different direction actually. So coming to this picture, so these are the domains here. This is unmagnetized because H is equal to 0. So whenever you have to apply an external magnetic field, then here in this domain, say this is a first region. So this is this domain, the direction of this domain is parallel to the direction of the applied magnetic field, so that it increases, the size of the domain is increased. But coming to this domain, here the direction of the domain is opposite to the direction of the applied magnetic field. So the size of the domain is decreased here. Okay, so magnetized by the domain growth. That means here the by the motion of the domain walls, the size of the domain is increased by the rotation of domains. So the rotation of the domains is observed under the application of a strong magnetic field. So that means the domains are rotated here. So this domain is rotated. So this domain is rotated. The rotation due to here magnetized by a domain rotation. So rotation of the domain is also observed here. So how these domains are rotated here? This is one domain. So this is another domain. So these two domains are separated by a block wall or domain wall. Say the domains are rotated here. Okay. So because of here motion of the here okay, the motion of the domain walls, and because of the rotation of the domains, so the material is magnetized. The ferromagnetic material is magnetized because of the motion of the domain walls and rotation of the rotation of the domains. Because the motion of the domain walls means the domains, those domains which are having okay direction parallel to the direction of the applied magnetic field. So they're having tendency to increase their size. That means those domains they're having okay increased their size. Whereas by the rotation of domains also, so the domains are rotated here. So because of these two, the given ferromagnetic material is magnetized. So during this magnetization, you have to observe four types of here energies exchanged. That means energies involved in the domain growth actually. So that is exchange energy, crystalline energy, and domain wall energy, and magnetostriction energy. So that is observed here, exchange energy and magnetic energy or magnetostriction energy. So these are only like equations actually. They are not necessary, but we should learn about. Okay, we should know about this one. So during the magnetization of the material, the energies involved in the domain growth is only four types. So that is exchange energy and magnetic energy and anisotrope energy and domain wall or black hole energy. So among these four here, anisotrope energy is very important because here during the magnetization of a domain, here each material which is magnetized in different directions. That means consider any ferromagnetic material just like iron, cobalt, or nickel. Say consider iron, it is belongs to BCC structure. Consider nickel, it is belongs to here. It is okay. It is also BCC. Of course, nickel is FCC structure here. But here, yeah, coming to BCC FE. This belongs to BCC structure, body centered cubic. It has different directions. That means the magnetization existing in the ferromagnetic material iron, so that is different in different directions. That is 100 direction, 110 direction, and 111 direction. So in this ferromagnetic, in this iron, so 100 direction is it is called easy direction. That means in this direction it is easily magnetized, but along this direction 111 it is hardly magnetized. So it is a hard direction. Whereas coming to nickel, say here 111 easy direction, but 100 is a hard direction because these are crystals here. So these crystalline solids, these ferromagnetic materials which are having crystalline structures, BCC and FCC and simple cubic, okay, etc. So these the crystalline solids, these crystalline solids, that means ferromagnetic materials which are magnetized in different ways in different directions. So these each ferromagnetic material, it has an easy magnetization direction and a hard magnetization direction. The excess energy required to magnetize a specimen in a particular direction, however that required to magnetize in the easy direction is called crystalline anisotrope energy. And domain wall or black hole energy. Domain wall creation involves energy which is known as domain wall energy or black hole energy. So of course these are energies involved during the material is magnetized, ferromagnetic material is magnetized, okay, and the application of external magnetic field. So mainly because of motion of the domain walls and rotation of the domains, the material is magnetized. That means the magnetization is produced within the material because of these two. And during magnetization process, the energies involved in the domain growth is here these four. And okay, so this is about the Weiss domain theory. And coming to next one, magnetic hysteresis behavior. Because these ferromagnetic materials which are having a very important property, that is magnetic hysteresis. Okay. Now we will learn this magnetic hysteresis in our next class.